Welcome back, Science 10. This is the last assignment in the FM3 booklet, and it involves drawing free body diagrams. And the two pages you are to go to are listed at the top of the page. And on one of the pages, you're supposed to run through this interactive demo here, which gives you practice looking at free body diagrams and looking at forces involved, etc. So I thought maybe I'd run through that with you, and just to ensure that you understand exactly how to do this, because it can be a little tricky. So here it is. It's under the Launch Interactive, and it's called Free Body Diagrams. And so you start the demo, and there's 12 situations that you have to run through. So I thought if you want to run through them yourself, then if you run into any difficulty, you could look at this video and see exactly how it works. So here's the first situation. The football is moving upward and rightward toward its peak of its trajectory. Ignore air resistance. So you're going to draw all the forces that are involved. Now, the football is moving, so you're not throwing it. It's already been thrown. It's in the time scheme of just simply going upwards. So the only force that's really going to be applied there is gravity. There's nothing else pulling it. So if it's at the top, gravity is always pulling it down. So if you throw it and it's speeding upwards, but as soon as it leaves your hand, it's slowing down, slowing down, slowing down, slowing down to a stop, turning direction, speeding up, speeding up, speeding up. So gravity is the only force that's being applied there. Okay? Let's see, situation 2. A downward moving skydiver who has just opened the parachute is slowing down. Diagram the forces on the skydiver parachute combination. So, of course, if you jump out of a plane, you're going to experience gravity. And there's an upward force too. If you jumped out of a plane, you would feel air resistance, air pulling on you. And of course, the further you fall, the more and more air resistance you feel. So this is actually going to get larger and larger and larger until you slow down. So you can see there's an unbalanced force here upwards. So if you're falling out of a plane, you slow down until eventually these equal out, and then you fall at constant speed. And in parachute language, that's called, or skydiver language, that's called terminal velocity. Situation 3, a hockey puck glides to the right across the ice at constant speed. So that tells you that all the forces are going to be balanced. So of course, gravity, since the puck is on the surface of something, there is an upward normal force, and it was already pushed, it's already in motion, so, and it's frictionless, so we can assume that there's no friction because it's ice, and we're not applying a force, so it's just simply moving like that, moving to the right. Remember, it's a snapshot of it already moving. We're not concerned how it got moving. Situation 4, a downward moving skydiver is falling at constant speed. So of course we have gravity, we have air resistance, and constant speed means there's no unbalanced force, there's no acceleration therefore, so that's all we have operating on there. Situation 5, let's see. The cabin of a small freight elevator is secured by a motor cable and is moving upward with constant speed. There's no contact between the cabin and the elevator shaft. Ignore air resistance. Well, of course we have gravity. And we're not concerned about the guy in the elevator, it's just simply the elevator itself. So there is an upward movement, and let's see, it's attached to a spring of some kind. So the downward force of gravity is balanced by the upward force of the spring, and it's moving at constant speed, therefore it's not speeding up or slowing down, therefore there's no unbalanced force on it. Oh, I guess maybe that could be tension instead of spring. Yes, so they used rope instead of spring. Situation 6. A football originally kicked at a 40-degree angle is at the peak of its trajectory. Now at the top of, the football is going to be stopped for a small moment in time, so you may be tricked into putting down zero forces, but guess what? There is gravity, and the moment that football leaves your hand, it's slowing down all the time. So it leaves at its top speed right when you release it. It's slowing down, slowing down, slowing down to a stop, and changes direction and speeds up, speeds up. So we just have gravity operating on it there. Situation 7, a sledder has reached the bottom of the hill and is coasting to the right while slowing down on loosely packed snow. Ignore air resistance. So we have gravity for sure. It's on the surface of the snow, so we have a normal force. Now it's moving to the right and it's slowing down. So there's no applied force on it. It's slowing down. So of course, what's causing something to slow down that's already moving? Friction. So you can see the unbalanced force is working against you, which causes it to slow down and go to a stop. It's very similar to that bobsled or that sledder interactive that you did earlier on. Situation 8, a rightward force is applied to a crate to push it across the floor at constant speed. Ignore air resistance. So of course we have gravity, it's on the ground, so we have a normal. We're pushing it to the right, so we do have an applied force. And it's constant speed, therefore we must be counterbalancing friction. So we're not concerned how we started to move it. We're just taking a look at this scenario of it already moving, in which the applied force is equal to the friction force, balancing, and up and down are balanced as well. So that's the scenario there. Situation 9, a rightward force is applied to a dresser to accelerate it to the right across the bedroom floor. So it's very similar to the previous one, except this time it is accelerating, which means that there is an unbalanced force. So friction working against us, applied force looking to the right. Now to ensure that I have an unbalanced force to the right, which causes it to accelerate, click on that arrow, make it a little bit longer, so we can see that up and down balance. Friction will balance some of the applied force, but there'll be a little force left over to cause it to accelerate due to an unbalanced part of that force. Situation 10, the cabin of a small freight elevator is secured by a motor while the cable is moving upward while slowing down. There is no contact between the cabin and the elevator shaft, etc. So downward, we have gravity. Upward, we have tension because it's being pulled up with the rope. And we're told that it is moving upward, but it's slowing down. So you must have an unbalanced force working against it. So that tells us that our force of gravity is larger than our tension force, because we're already moving up. We're looking at the snapshot of it moving already upwards, but it's slowing down. So the upward force balances part of the downward force, but we have extra downward force to slow it down until it reaches a stop. Situation 11. A rightward moving car is skidding to a stop across a level roadway with locked wheels. Ignore air resistance. Okay, so as usual, we have gravity pulling downwards. It's on the ground, so the ground is pushing up with the normal force. It's moving to the right, but we're not accelerating. We're not putting on the gas pedal. We're slamming on the brakes, actually. So what that is going to do is just simply supply friction. So we're moving to the right, unbalanced force working against us, so it's going to slow down until it comes to a stop. And situation 12, a softball player does a head-first dive and is sledding to the right across the infield. Ignore air resistance. This is very similar to the car. So you're on the ground, so you have, where am I here? Normal force upwards, gravity pulling downwards. You're not running to the right, you're just sliding. So to the left you'll have friction, and that should be it. Okay, so if you have any trouble, come back, look at these videos again, and hopefully you'll be able to do the assignment after that, which is labeling your own free body diagrams. Okay, we'll see you again.